Welcome AP Statistics. This is part 3 of chapter 12. We are going to put all the pieces together now. We are going to design an experiment. Let's have at it. So we have an ad for OptiGrow, a very creatively named plant fertilizer company. It makes plant fertilizer, and it claims that this product will grow juicier and tastier tomatoes. You would like to test this claim and also wonder whether you may be able to get by with half the specified dose. So do you need the full dose, or can you get away with half a dose to produce desirable tomatoes? How can you set up an experiment to check out that claim? Okay, so to boil it down, we want to see if this fertilizer improves the quality of tomatoes, and we also want to see if we can get about the same result with half the specified dose. So that means that we're going to have more than 2 levels of the variable fertilizer. Okay, so let's see how we can set up this experiment. Well, first thing we want to do is state what we want to know. We want to know whether the tomato plants grown with OptiGrow yield more desirable tomatoes than plants raised in otherwise similar circumstances but without the fertilizer. And now we're going to state the response variable and how it is measured. I'm going to evaluate these desirable qualities of tomatoes by asking a panel of judges to rate them on a scale from 1 to 10 in the desirable qualities. And now we want to specify the levels of each factor and list the treatments. The factor is fertilizer. Okay, so that is the explanatory variable, specifically OptiGrow fertilizer. Okay. I will grow tomatoes at 3 different factor levels. Okay, so our explanatory variable has 3 levels. As I've stated before, some with no fertilizer, there's our control group. Some with half the specified amount of fertilizer, that is our first treatment. And our second treatment is the full dose, the real deal of OptiGrow. And those are the 3 treatments. And then we state the experimental units. The experimental units are 24 tomato plants of the same variety from a local garden store. And hopefully those plants are as similar as possible to avoid bias. Now we want to observe the principles of good experimental design. As before, we don't need to block quite yet. There will be an instance later on in which we'll need to block in this experiment, but we don't know that yet. So we'll observe the first 3. We're going to control first, control any sources of variability you know of and can control. So the book says that they will locate garden plots near each other so that the plants get similar amounts of sun and rain and experience similar temps, and weed the plots equally and otherwise treat the plants alike. So we're going to treat the plants well and treat them alike. Then we can replicate results by picking, or rather placing, more than 1 plant in each treatment group. That seems obvious. We'll use 8 plants in each of the treatment groups. 8 for the control treatment, 8 for the half-dose treatment, and 8 for the full-dose treatment. And finally, we randomize. We'll randomly assign experimental units to treatments to equalize the effects of unknown or uncontrollable sources of variation. And here is how the randomization will be accomplished. We can use random numbers, all right? To randomly divide the plants into 3 groups, I'll label the plants with 0, 0 to 23. I'll look at pairs of digits across a random number table, so we can use a random number table, random number generator, any variety of randomness that we have seen before in class. The first 8 plants identified, ignoring numbers 24 through 99 and any repeats. This is using a table of random numbers, of course. We'll get no fertilizer, the next 8 a half dose, and the remaining plants the full amount. And that's how we can randomize into those 3 treatments. Then we want to specify any other experiment details. And this is just kind of an odds and ends section, right? So we grow the plants until the tomatoes are mature. We don't want to test the tomatoes prematurely. And as judged by reaching a standard color, harvest the tomatoes when ripe and store them for evaluation. And then I skipped ahead to this a little prematurely. Specify how to measure the response. You could set up a scale of desirable qualities, one for the juiciness and one for the tastiness of the tomatoes, and the taste testers can use those scales. And we're going to have several people taste slices of tomato and rate them. This is a pretty big operation here. You got to find taste testers for this. And this is a model that we could use. We have 24 tomato plants from a garden store. We have a group right here of 8 plants, group right here of 8 plants, group right here of 8 plants, and we randomly assign to these 3 groups. To this group of randomly assigned plants, we have the control treatment, so we don't give any OptiGrow fertilizer, we just grow them the old-fashioned way. And group 2, we have a half dose of OptiGrow, and group 3, we have the full dose as the bag suggests. Assuming this fertilizer comes in a bag. And then we compare the desirable qualities. All right, so this is a good layout of the experiment straight out of your textbook. The textbook does a really good job of laying out how to design an experiment properly. All right, now we're going to interpret the differences between groups. All right, here's a gentleman who knows a little bit about fertilizer and how to motivate a team. So it may well be that the tomatoes with more fertilizer have better juiciness and taste, but are those qualities significantly better? So say our experiment turned out that yes, OptiGrow does seem to produce better tomatoes, but are they significantly better? That's a key word here. I will often say to students that the 2 most important words in statistics are independent, which we will see a lot, especially as we get to the last, say, third of the year, and significant, okay? Independent and significant. Those are the 2 biggest words in statistics as a whole. So significantly better. Differences between groups in an experiment are said to be significant when the differences are so great that they could not have occurred randomly by chance alone. All right, so the odds of the tomatoes, if they're significantly better, they are so much better than without the fertilizer that we didn't just get lucky and get the best tomatoes ever by accident. No, the difference is significant when differences between the control and treatment groups in this case are so great that they could not have occurred randomly by chance. So even if the fertilizer had no effect on the tomatoes, we can expect some variation in the scores. Some tomatoes are just naturally better tasting than others. However, if one or both of the fertilizer groups varies a lot relative to the control group, it must be due to more than just random chance alone. There's some cause and effect going on, and that's the power of an experiment. We can show cause and effect. So since we performed an experiment, we can conclude that a significant difference in the quality of tomatoes is likely due to the difference in treatments. This is something we cannot do with observational studies. We cannot show cause and effect with observational studies, only association. But with a well-designed experiment in which we can control and in which we can replicate and randomize and block if need be, with a well-designed experiment, we are capable of showing cause and effect. And that is the power of an experiment. So small differences are associated with random chance. We should expect little differences, even if there's no major effect from this OptiGrow stuff. But if there is a significant difference, that is more likely associated with the treatments themselves. We don't get significant results by chance. We should expect insignificant results, but significant results, that's not by chance. So here's the big question. What's the difference between insignificant variation and significant variation? What separates just getting a couple lucky good tomatoes in one group as opposed to another, and a really big noticeable difference that we can attribute to one of the treatments? So to understand what separates a trivial difference between groups and a significant difference, small difference versus big difference, we could consider flipping a coin 100 times. Here's a basic example for how to determine significance. If we got 54 heads out of 100, this is not a huge difference from the 50-50 split that we would expect. So we would expect to see 50 heads, 50 tails. That's the most likely result. However, 54 heads is very reasonable. Like we would not be surprised if we got 54 heads and 46 tails out of 100 coin flips. And we would be silly to say that this coin favors heads, all right? It just favored heads in these 100 flips, but is it going to favor heads in general? That would be a long shot. That's very unlikely. However, if we got 94 heads out of 100, this would be honestly nigh to impossible. And we'll be able to model this later in the year, how impossible that would be. If we got 94 heads out of 100, that would be very unexpected. It would also be a significant difference from the 50-50 split. So if our difference between what we expect and reality is small, then that's an expectable difference, all right? We're not going to get a perfect 50-50. That's the most likely result, but it's not terribly likely. It's not terribly likely relative to all the possibilities that we could get. But a 94-6 split, that's almost impossible. Like that, we could all try flipping coins for the rest of the year, and we're not going to get a 94-6 split. That's not going to happen. That would be a significant difference, and we'd have to ask ourselves whether this coin is weighted in some kind of freaky way. All right, the favoring of heads with such a coin is not due to chance. There must be something interesting about the coin. This coin's rigged to land heads. It's kind of like Two-Face's coin, if you know the reference from Batman. Now we're going to talk about placebos. All right, you may be wondering what a placebo is. And if you know what a placebo is, you might be wondering about how we can use it in statistics. Placebos are one of the neatest things that we can do in the design of experiments. Let's begin. A fake treatment that looks like one of the treatments being used is called a placebo. Okay, so a placebo is a fake treatment. It looks like an actual treatment. It does not look like a control treatment. It looks like an actual legit treatment, but it's not. That's called a placebo. Placebos are the best way to, and this is a technical term, blind subjects from knowing whether or not they receive a treatment. And this is why we often use a placebo as a control treatment, okay? So if we want to disguise the control group, we could make the control group think that they're receiving a treatment. This is especially effective for human participants. This is really almost exclusively effective for human participants. So we can make sure that a difference we'd be accounting for is not just in people's heads, like it's an actual cause and effect difference. Sometimes subjects improve after receiving a placebo, and this is called the placebo effect. We talked a little bit about blinding on the last slide. Let's talk a little bit more about the process of blinding in statistics. When we know that we are taking part in a study, it's difficult not to let that affect our behavior in some way. This is known as the Hawthorne effect. Now, that's a kind of an obscure name. Where does that come from? Well, in the early 1900s, when statistics really started taking off in the social sciences, there was some research being done about workers in a factory called Hawthorne or in a place called Hawthorne, I'm not sure. I think it was the name of the company. And the workers realized that they were being studied by researchers and their behavior changed to the point where the results were kind of trash. And so this tendency for people who know they're being studied to behave differently has since been called the Hawthorne effect. So how do we prevent against the Hawthorne effect? Well, suppose we were determining which type of lemon lime soda students like best. We could sample some students to taste the beverages and cover the label so students aren't influenced by a brand name. So you can probably think of a couple brand names of lemon lime soda out there. So one way we could blind is to make sure that the sample of students who are taste testing the beverages wouldn't be able to see which soda they were drinking. This strategy is called blinding, right? That's what blinding is. There are two classes of people who can affect the outcome of an experiment, two reasons we would want to blind. Those who are taking part in producing or gathering results, and those are subjects, treatment administrators, etc., who are physically present as the data are being collected, so folks on site as the data are being collected, and also people who evaluate results, judges, physicians, etc., who can assess the quality and effectiveness of the treatments. So you have the first group of people who are kind of boots on the ground, as it were, like they're taking part in the actual collection of the data. And then you have the evaluators down here. And both of these sets of individuals, ideally, we would like to blind. We would like to make sure as much as possible that we are mitigating the Hawthorne effect from happening, from things getting messed up by people, subjects, participants knowing that they are being studied, all right? Or knowing that they are taking part in a study, okay? So we want to blind these two groups of people as much as possible. If one class is blinded, the study is said to be single blind. If both classes are blinded, the study is said to be double blind. All right, so if we were to just blind one of these classes, folks with boots on the ground taking part in the study itself, or just blind the evaluators of results, that would be single blind. But if we were to do both, which is ideal, that would be double blind, like our friend Patrick the Pirate. So let's relate this to our scenario involving the tomatoes. So let's consider the study on the tomatoes. If we were to ensure that the judges didn't know which tomatoes got the fertilizer, that would be single blind. That would be blinding these folks, the evaluators of results. If we were also to ensure people administering the fertilizer to the tomatoes didn't know whether they were administering fertilizer, water, fake fertilizer, there's a placebo, or half fertilizer, half water, the study would be double blind. So not only are we making the judges blind, not knowing which type of tomato they're evaluating, but we would also be blinding the people with boots on the ground, which adds an additional prevention against the Hawthorne effect. So we'd be blinding the ones taking part in producing or gathering the results and the ones evaluating the results if we were to double blind. Now, this is a fascinating example of blinding by misleading. I'll leave this up for a few seconds. You can pause the video, read through this example. I find this interesting, maybe a little morbid, maybe a little humorous. You decide. All right, I'll assume you're good to go. Let's continue. Let's apply our knowledge on blinding. In our experiment to see if the new pet food is now safe, back to this pet food example, we're feeding one group of dogs the new food and another group of food we know to be safe. Our response variable is the health of the animals as assessed by a vet. And the question is, should the vet be blinded? Why or why not? If so, how would you do this? And here's an interesting question. Can this experiment be double blind? Would that mean that the animals wouldn't know what they're eating? Interesting question. That one's a little tricky. First question's not so bad. That second question's a little tricky. Think this one over, see what you come up with, and compare your result to the result in the textbook. All right, I'll assume we're ready to continue. Here we go. So, whenever the response variable involves judgment, it's a good idea to blind the evaluators to the treatments. And this one absolutely involves judgment because we're asking a vet to evaluate a pet, okay? The veterinarian should not be told which dogs ate which foods. That can reduce bias. And here's the answer to the extra credit. There is a need for double blinding. Interesting. In this case, the workers who care for and feed the animals should not be aware of which dogs are receiving which food. Again, like the people who are evaluating the results, when we can, it's nice to evaluate the people with boots on the ground. Now, you can tell a dog whatever you want. The dog's not going to make heads or tails of what you're saying, most likely, unless they're a very smart dog. Maybe a border collie would know, but your typical dog is not going to make sense out of it unless they're a super genius dog. I don't know, maybe Mr. Peabody would know. If you know that reference, by the way, give yourself a plus eye. So those who care for and feed the animals should not be made aware of which dogs are receiving which food. We'll need to make the safe food look as much like the test food as possible, and that's how we can make this experiment double blind.